Okay, let's build off of what we looked at primarily in section 9.1. And we've got the fundamental idea here now, right? We've got flux that's varying at a certain rate, sinusoidally, and this varying flux is in proximity to a coil, and it's inducing a voltage. All right, so let's take this to the next step. And remember, what we're doing here is we're building a transformer. We're putting the pieces together, and we're building a transformer. Okay, so in figure 9.2a, what we have is a coil, has a certain number of turns on it. We'll call that N turns right here. And it's connected to a sinusoidal AC voltage source. And we're going to call that, since it's a source voltage, we're going to call that E sub G. And E sub G produces a current, and there is a reactance in the coil. We're going to ignore any resistance in the coil, and we'll just simply look at inductive reactance that we're going to call X of M. And it's going to draw a current that we're going to call I sub M. And we can see the current here. And then this is the applied voltage. Now, there is a slight difference between what's applied and what the coil sees, but we won't go into particulars of that. But what I do want you to know is that this induced current, I sub M, will lag the voltage by 90 degrees. And we know that's a fundamental of an inductor, right? Voltage leads current by 90 degrees, or we could say current lags voltage by 90 degrees. Okay, now a couple other things. Notice that the current mirrors the flux. Okay, and again, we'll look at the difference between E sub G and just E, but you can kind of maybe get an idea of what's going on there, because there's a difference between what's applied and what's seen at the coil. Now, he goes on to say the detailed behavior of this circuit can be explained by telling us that I sub M produces a sinusoidal magnomotive force, that we have looked at already, and that is simply number of turns times the current, okay, which in turn creates this sinusoidal flux. Okay, so this creates the flux. All right, and consequently, I sub M is called the magnetizing current, and the peak value of this AC flux is given to us as this, and that's the thing that we used in our equation earlier. The flux induces an effective or RMS voltage across the terminals of the coil. Okay, so here's the thing, and this may seem sort of trivial at this point, but this is an induced voltage. This is an applied voltage. Okay, this times that number of turns times the current causes this induced voltage. All right, it's important that we get that if we're really going to understand how a transformer works. Okay, the flux induces an effective voltage across terminals, which is given by our earlier equation 9.1. On the other hand, the applied voltage and the induced voltage must be identical in value because they appear between the same pair of conductors. Okay, so if they're identical, I can now write this equation as E sub G, right, as source, all right, times this, okay, because this has to be the same, right? It has to be. It's just that this is called an induced voltage and this is a source voltage. our equation 9.1 was the equation for an induced voltage that was given to us. Okay, and so we've rewritten that as this, and then what I can also do is I can take this and I can solve it for this maximum flux value, and that is going to get me this equation, which is 9.2 here. Okay, it's just this equation solved for the peak flux in that place. So if we look closely at this equation, what it tells us that for a given frequency and a given number of turns, in other words, these are constants, this voltage will vary in proportion to the applied voltage. This means that the applied voltage, if the applied voltage is kept constant, the peak flux must remain constant. All right. So, you know, just looking at the obvious here, right? We're just looking at this equation and making these observations. So he says, what if we gradually insert an iron core into the coil? So we're going to find this iron core, and we're going to insert this into this coil. Now, according to this equation, we have to trust our equations, the peak value of the AC flux will remain absolutely constant during this operation, and it will maintain this value. Okay? So this equation holds true. These are constants, and this is varying proportionally to the applied voltage. And so retaining the original value and the core is completely inside. So in effect, the flux increased as we would expect because we're focusing it, right? The induced voltage would increase also. Okay? But this is impossible because we said that this was the case. The induced is equal to the source. And so this is fixed. Okay? I mean, if these things are all true, induced is equal to source, but we're thinking and we understand how this, you know, ferromagnetic inserted into this coil, you know, it concentrates the flux. So what does this mean? I mean, where do you go with this? So where we go with this is this last paragraph here in the first column on page 185. He says, for a given supply voltage E sub G, the AC flux in figures 9.2 and in now, let's look at 9.3, okay? Here is this same problem. Here's our coil. And now we've placed this ferromagnetic core into this problem. He says, you know, the flux is the same here as it is here. Okay, so that sort of goes against what we think should be the case, but here's the deal. Here's the deal. This has to be true, all right? What we're getting, he says, is the magnetizing current can be smaller to maintain these same values when the iron core is inside the core, or coil, I should say, okay? So what he's saying is we've made a better device here by putting this ferromagnetic inside of it because we're getting the same induced voltage at a cost of less current. So we can use less magnetizing current to get the same voltage. So he says to produce the same flux, a smaller magnetomotive force is needed with an iron core than with an air core. Consequently, the magnetizing current is much smaller in 9.3 than it would be in 9.2 without the core. Okay? So one thing we'll look at as we get into more particulars of our transformer is that we can make transformers better with materials that we supply, and this is one example of that. Okay, so let me stop here before I drag this on too far, and then I'll do a second video where we'll work example 9-2.